Se tivesse transmitido renda per capita, é diferente.
Alguma coisa bom.
Agora 55.
Good afternoon, everybody. Can you see the screen?
Antes do celular todo quebrado, com todo lascado, agora se acha.
Could you please confirm if you are seeing the screen? Okay, thank you. Okay. Can I start here?
Yeah, sure.
Okay. Good afternoon, everyone. I'm Lucia, and today I will talk about exploring the so-called portals to the dark sector and the famous WISP, that are the interacting slim particles, also called are conformed by the axions and the dark photons. Firstly, I will talk about the theoretical motivation. After that, I will talk a little bit about the dark photon. And after that, I will explore some general aspects of the axion and axion particles. Let me just set here. Okay.
Você está compartilhando no StreamYard, tá? No StreamYard, está compartilhando?
I think it is sharing. Could you please confirm in YouTube? So guys, I just cut some slides from this presentation because it was taking a lot of time, but I will explore the most general ones.
Só em você, na tela do StreamYard. Compartilhou só no Meet. Eu tenho que compartilhar no StreamYard.
No StreamYard. Você tem que ali, present.
Okay.
Present.
Now share the screens here. Okay. I will start again. Good afternoon, everyone. Today I will explore the so-called portals of the dark sector and the WISP that are conformed by the dark photons and also the axions, the particles. I will talk about the theoretical motivation. I have talked with some new members of the group, and they have not worked with the dark matter, so I will give an introduction and the motivation of why it's important to explore these particles. In this case, I will talk about the dark photon and also axions and axion-like particles. So as we know, the standard model of particle physics is a successful theory that describes 3 or 4 interactions: strong interaction, weak interaction, and electromagnetic interaction, and was formulated by Sheldon Lee Glasgow, Abdus Salam, and Steven Weinberg. As you know, this theoretical framework it predicts very good results that were confirmed later by some experiments, such as the mass of the W and the Z boson. But unfortunately, even if it is a successful theory, it is not enough to explain some other phenomena, such as the dark matter. In this case, I will introduce a little bit what is some of the main evidences of the dark matter. Here, I just put 5 of them. We have the galaxy rotation course. I know some guys have not studied this, so I will just explain a little bit. What happens with the galaxy rotation course? Vera Rubin and Ken Ford, they observed some galaxies, spiral galaxies, and they found that they expect that the stars that were in the string of the far of the central galactic, they expect that they rotating more slowly than the other ones that were near of the galactic center. However, what they have seen is this did not happen, and they observed that maybe this was this happened because there was a kind of matter that was affecting the gravitationally to those stars, and they were like influenced in the rotation of those stars. So they found these galactic rotations, where you can see here the line in the above of the plot, the observation from the starlight, and here you can see the observation from the 221 cm hydrogen. This is just possible if you include dark matter in this phenomena. Here we also have the CMB, that when you analyze the power spectrum of the fluctuations, you can see some peaks that told you what is the proportion of the dark matter and baryonic matter, and also give us information about the curvature of the universe. We also have here the bullet cluster that has baryonic matter in form of gas, warm gas. When you observe this gas through some telescopes, you can see the X-rays, and it is we are able to differentiate what is the distribution of the baryonic matter. And you can see that there are like a kind of matter that is not interacting, and the center of the mass is a kind of deviated of where we expect they stay. So we also have the Big Bang nucleosynthesis that gives us information about what is the quantity we expect of the elements. Indirectly told us that following the lambda CDM model, this quantity of matter is not enough to explain other phenomena. Finally, I just add the large structure formation, where you can see some cluster and cumulus here, and also some spaces in a dark color. And this told us that when you have some simulations, you need dark matter in order to get the structure formation with that velocity we are observing today. Because if we don't have dark matter, if we don't include dark matter, and we just do that simulations of the evolution of that structure formation, the baryonic matter is not enough. Maybe that large structure formation evolve more slowly that we are observing right now. So I talk about the evidences, and now I have, according to the lambda CDM, we have 68.3% of dark energy, and we know that there is a kind of 26.8% of dark matter, 40.9% of the baryonic matter. We know that there are so many candidates that covers masses between 10 to the minus 22 eV to 10 solar masses. It confers ultralight dark matter, light dark matter, the so-called WIMPs. We also have the composite dark matter, and also primordial black holes, among others. But I think that is not in full screen. Okay. But even with all those candidates, we also are exploring some particles that are called portals that allow us to connect the standard model particles with the hidden sectors, where we expect to find the dark matter. So in this case, in this presentation, I will talk about the vector and the pseudoscalar. In this case, the vector will be the dark photon, and the pseudoscalar will be the axion and axion-like particle. These particles will have a function of a kind of bridge between that two worlds. So I will start with dark photon. I could some calculations because it was a very large one, but I will try to explain very quick. This dark photon was proposed originally by Holden. And here in the first equation, putting just how is the kinetic part of two abelian gauge bosons. Here, one boson is denoted by A, and the other one is denoted by B. And here we can see that they can like a kind of mix through a new parameter that is called epsilon. This epsilon in this theory is called kinetic mixing. Here, if we just put connect those gauge bosons with the current of the standard model at the dark current, we can see here, and this results in a Lagrangian, where you have the current of the standard model, Jme, with the other boson of the dark sector, that is the V. And here we have vice versa. In this case, we have the dark current coupling with the photon of the standard model. You can diagonalize these terms as is shown here, and you can rotate, apply the rotation matrix, and you can obtain this equation here. As I said before, it is important to take into account that this epsilon that allow us to connect both currents. This is the Lagrangian we obtained here. And in this case, we have to explore two cases. The first one is the massless, and the other one is the massive. In this case, exploring the massless one, we can choose arbitrarily the sin of theta equal to 0. We can couple here the standard model current with the dark boson through this kinetic mixing and the coupling of the standard model. On the standard model coupling with the photon, you can see that they are mixing here, and you obtain this Lagrangian here, and this is the coupling between this current with the dark boson. In this case, this is the dark current, and this is the coupling of the standard model current with the dark boson. And here is just the current, the standard model coupling, current coupling with the photon of the standard model. It sounds repetitive, but maybe it's important to understand this. In this case, if we choose arbitrarily the sin of theta equal to epsilon, and here the cosine of theta equal to the root of 1 minus epsilon squared, you can obtain this different case. In this case, the dark sector current is coupling with the photon of the standard model, and you obtain here those couplings here. So for the massive dark photon, I forgot to say something. In this case, you have to take into account that this kind of dark photon, massless, it is just applicable if you use UV models and you find something called Millis charge. But when we pass to the massive dark photon, the behavior is different. We are just assuming that the dark photon has mass. It can be obtained from the symmetry, spontaneous symmetry breaking, where you can produce a dark photon and also a dark Higgs, or you can also generate the mass with the Stuckelberg mechanisms. This Stuckelberg mechanism, I'm not going into the details, but with this mechanism, you don't break the symmetry, but you include a new scalar that is called the Stuckelberg field, and you can in some way moderate and in some way share the information of the mass to the dark photon, but it is a very complete a very different mechanism of the symmetry breaking. Here, for both cases, we can choose this arbitrarily angle And here, this delta we are seeing here, in this case, comes from the Stuckelberg mechanisms, but for both cases, it's applicable. In this case, this is the proportion between this boson and the boson of the dark photon. Here, we don't have the freedom of rotating the fields as the last case, and the Lagrangian just becomes, in this Lagrangian we are showing here, to finally get, in both cases, this current here that is modulated by the coupling of the standard model with the photon, modulated by an epsilon, that is a kinetic mixing I told before, the standard model current, and also the dark photon. So this dark photon, as I told you before, can have a kind of character of the bridge between both sectors. But it is also a candidate of dark matter. In this case, we are assuming just that it is like a kind of mediator. And we are assuming the dark photon is massive, is more massive than 2 times the mass of the dark matter. In this case, we are assuming this annihilation channel, and we obtain this cross-section. This cross-section, as you can see, here is modulated by the coupling I told you before, and has this form. When you apply the non-relativistic limit, you find that this is the result for the average sigma v. And here, in terms of the omega chi h squared, you find this relation here. Currently, there are so many searches for the dark photon, and I am showing you the existing bounds for different sources. In this case, in green, you can see the astrophysical sources. In blue, you can see the cosmological sources we obtain from the analysis of the CMB. And here in purple, you can see all the experimental efforts to find the dark photon. In this case, we are right now developing a paper where we are exploring this area that is an explored area, and also we are covering this one that can be used, our experiment, in this case, our proposal, as a precision experiment test. In this case, as you, sorry, I didn't mention, here in the x-axis, you see the dark photon mass in EV, and in epsilon, you can see the kinetic mixing in epsilon. Now I will pass to the axions and axion-like particles. I have to admit that this is a little bit complicated for me, but I try to understand in order to explain to you. So in this case, we have the dynamic term of the gluons here in the first one and the fourth one here. Here, this term, this respects, doesn't violate the CP and T symmetries, but the standard model allow us to include this term here, that is theta g squared over 32 p squared, and here we have this gluonic strength tensor. The problem is that this term allows the CP violation, and we have not observed this CP violation, and here it predicts that this CP violation is very large. This is just notation to understand how this can be written, some properties for that strength tensor, and also the dual one. And here, if you have the product here, you can conform this derivative of the current that is also called the Chern-Simons current. So, what is the problem? It allows.
When you said the about the last term. So then violates CP violation or PT? Because
No, CP violation. It also it respects the C, violates the parity, and also violates the time reversal, but also
all the CP.
violates the CP. So I forgot to put it here, but also violates CP. So this is allowed by the standard model. The problem is we don't measure this kind of violation. When you try to measure this in the electric dipole momentum of the neutron, that tell us the distance between them, the charge, we found this upper limit, and this upper limit lead us to expect that this parameter theta is less than this 10 to the minus 10. If we multiply this, if we expect this result here, this term will be very, very small, but this is not according to the result, the experimental result. So we have the strong CP problem. So when you apply,
I didn't get this point. What is exactly the bound and what's exactly measured?
this is an upper bound that has been done for the experiments. And the experiments told us that this parameter theta, that is a kind of how much you are violating the CP symmetry, is given by this number. It should be smaller than this number. But the problem is that the standard model told us that the CP violation is large. So the experiment and the standard model, this term is not are not according.
But wait, so in the model, in the standard model, you have this data.
Yes.
But when you measure the theta,
But the
it
theta,
is greater than that
It
bound that you
should be
said.
almost one. What do you mean?
yeah,
by
it should be one,
Okay,
more or
I
less.
see, okay.
So it's very large in comparison what we are obtaining from the
Because
experiment.
if you just tell me that it should be larger, so I mean, data should not be there, or it should be irrelevant, or you know.
Now this actually modulates that we are violating the CP symmetries. So it exists and is large. In comparison with this number,
Or
is large.
something is missing, some kind of symmetry. Is that included?
Yeah, that's why I want to
Okay,
explain
because if it does exist a disorder, you should measure, but we don't measure.
exactly. The standard model prevents that we have to measure the CP violation. We should measure the CP violation, but we are looking from the results. The experiment result is that we are not obtaining that result. So that's why there is a kind of discordance between both results.
Sorry, just to clarify, the result that we get from experiments is this small number.
Yeah,
And what we expect from the theory is
is a large number, exactly. So, as you can see here, I didn't put the mass terms, but we do know that actually the quartz has mass. But when we try to apply a chiral transformation here, we have some rotation in those terms that I'm adding here. You have this transformation for the QL and QR. Just that when you do that chiral transformation respecting this this new parameter here that is it emerged from the masses, it adds other term that is violating also. So it's very confusing because I understood as that they are doing a kind of fine tune, trying to has a subtraction between the theta and the phi, but this is not happening. So what is the solution the community accept here, but it is not proved experimentally, is the PASCCO solution, because this term cannot vanish because we are giving mass to the quarks. I have to say that even if we don't conserve, even if we don't do that kind of rotation here, this phi that I'm putting here that is added to this term also emerged from the Yukawa interaction from the hip sector. So we cannot just vanish it. It exists and we cannot just ignore it. So it is a problem. The PASCCO solution, what say they add a new symmetry group called U1 PQ, and they transform a chiral transformation here for the quark, and they have a shift here when they just transfer this A, that is the axion field, over the scale of breaking. They call in the literature, and they have a shift here. When they have that kind of transformation, they just obtain this term here. And what does this term here? That this A over the FA is equal to minus theta, and they can just cancel both terms, and the CP violation is solved. But we have to take into account something, that when you do that and the PASCCO symmetry is breaking, you generate a Nambu-Goldstone boson. And this Nambu-Goldstone is boson is the axion. And this axion we expect that has at least a small mass. So below the scale of KCD of 200 MeV, in this scale appears the quark condensates in form of mesons, and those mesons break the symmetry and generates this potential I express here in this form. So taking into account this kind of the case of the pion, you can banish the term responsible, as I mentioned here. You just delete both terms, and you when the action is around the minimum, generates this mass for the action that can be modulated by the term of breaking. Yeah. So I don't know if you have questions until here.
I didn't quite understand this in the previous slide. Yeah, so
This
that
one.
A over FA equals minus theta. Is it enforced or something that you can derive in the theory? I didn't quite get that.
This is the field that you obtain after you break the symmetry, and after this is the scale of the scale of the symmetry breaking.
Yes.
In that scale, this is equal to minus theta, and you just vanish both terms.
Why is it
Enforced.
you enforce it to make
Mhm.
it? Okay.
Because you don't see, you don't measure. So basically, that's the idea that should be this guy, this axiom,
Okay.
that would break core your CP violation.
We're gonna address this in the course.
Perfect. Okay, we obtain this term of mass. We modulate it with this symmetry scale breaking here, and we also from this theory was derived this misalignment mechanism. That this alignment mechanism allow us to relate the action with the dark matter. So firstly, we have when the temperature was bigger than the scale of the KCD, that theta I mentioned before has a random value between the minus p and p. as the universe expands, the temperature just drops and was approximately the scale of QCD. The symmetry is breaking, and the action it kind of enforces effective potential here that is approximately this term of here. When you analyze the motion equation of this action field, here is the acceleration of the action field. You have here the parameter of Hubble, here is the velocity, and here have the potential. When you put, as I said, initially you have an arbitrary parameter here that was randomly. When the potential, when the symmetry was breaking here, this is enforced in some way to reach the minimum of the vacuum. And when you do that, you can see at this temperature that the energy density of the action can be expressed in this way. And this is exactly how the dark matter behaves, because here it decreases with the expansion of the universe to -3. Taking into account this, you can calculate for any case the dark matter relative density with this equation here. Taking into account that when you have symmetry breaking scale here for AFA, the mass will be light as what in comparison if this is very small. So you have to be careful because it can just mess up the quantity you are expecting for the relative density. In some models, I have seen the action is not just the component of the dark matter. It also appears to multi-component dark matter. So this calculation is just according to this one. And here this theta is the CP term I mentioned before in the previous slides. We also have the action-like particles. The action-like particles are very similar to the actions I mentioned before, but the problem, but they have just advantage because they are not made for solve the CP violation, but they have some behaviors very similar to the action one. In this case, the action-like particles are proposed in effective theories and other dimension theories. Also, they were developed in order to explain how I don't know how to, attenuacy? I don't know how to say that. Atenuação. Attenuation. I'm not pretty sure if this is the term. Attenuation coming from the gamma ray from the astrophysical sources. They are exploring in the community, experimental community, very different couplings between the actions and action-like particle with other particles, such as the photon. In this case, the plot I put here that is the most studied currently is with the photon. Here in the epsilon, we have the coupling between action and photon in GeV to -1. And here we have the mass of action and electron volt. As you can see here in yellow, we are considering just the quantum chromodynamics action. And here we have other experiments. We have, for example, the dark matter decay that just cover this parameter space here. We also have some constraints from astrophysical sources such as solar, global clusters, pulsars, etc. We also have some other experiments like superMAC, and others coming from the being done experiments and colisionadores. Esqueci o termo. And And this is the bibliography. I mostly put a hybrid of those bibliography, but the presentation was mainly based in this paper here that is Dark Photon, that is very complete. Actually, I fully recommend this paper in order to understand Dark Photon. And for the action dark matter, I have used the Jan Mambrini, also the white paper Action Dark Matter, and also I think maybe I didn't include, but the original paper where the Pesce Queen developed the solution for the CP violation. And it's all. I don't know if you have questions. No sé.
So I have one comment.
Mm-hmm.
So you can think about it. So as you now look, show that plot. See. So for instance, the community, especially the American community, tries to sell the idea that actions with couplings 10 to minus 20, 10 to minus 20, and masses 10 to minus 9, 10 to minus 10 are fine. There is no fine tuning. But if you invoke some non-standard cosmology in effect of 10, well, no, that's fine tuning, that can't happen. No. Wimps are wimps. You cannot invoke non-standard cosmology, makes no sense. Now you're tweaking things, making things ugly, and so it's a matter of taste.
The same for wimps.
And you also should be aware is that, so for instance, WIMPs have been driving the community for the past 20 years or so. And as the US lost the battle for the search for dark matter, and they shift their resources to neutrino physics, which is to build the Dune detector, then a large pile of money of the DOE, Department of Energy of the United States, would be like our Ministry of Science and Technology, something like that. They put all their money in the pocket of Dune, and then they don't have like a flagship dark matter experiment. They lost the battle to Xenon and Dawn and other big end-pons detectors, dark side, argon, something. So what they did, so they put the little money they had, relatively speaking, to search for something related to dark matter, but it would be low cost, because the only money they had. And that low cost would be axion-like, because axion-like experiments are much cheaper than WIMP-like experiments. You need a shiny through a wall experiment with a large magnetic field where you convert photons to axions, and that's what they have. And they had one experiment which is called ADMX, which is the most sensitive dark matter detection experiment for axions, which covered the larger masses, like above 10 to minus 6 or so, have been mostly excluded by ADMX. And since they lost the battle, one thing that doesn't happen in our Brazilian community, but in the US community is like this. Some group of selected people, they decide that a large part of money will go to Dune, and some fraction of the money will go to axion-like experiments. So all the theorists in the US, if they want to have money to do whatever, they have to work on axions. Here. If you don't want to work on axions, it's fine. But you don't get money to travel, you don't get postdocs, you don't get grants. But it's up to you. So now the US is axion-driven. And you see all researchers doing axion-related studies. Even the researchers who badmouth axions before, now they're axions are so interesting, axions are awesome. Yeah. And they also would talk down to black holes, primarily black holes is dark matter, and now they're popular. So, wow, primary black holes are.
But then it was, I mean, for the light numeral black hole, it was basically excluded in most of the primary space. But finally, a guy from Germany, he revived it using general mechanism called inversion. And then now they can have, it's very interesting by the way, but then you're gonna have light numeral black hole still alive today, still survive. So you can use these guys to probe, for example, the photons, axions. Instead of just using super radiance as the last spot, you can also play with the Hawking radiation, for example. It's interesting. There are a lot of things.
And the key things for you guys is that it doesn't matter what we think. It means that we have to follow the stream. So if you want to shine at the international level, you have to follow the stream. Period. That's it. But if, remember that there are very different things. One thing is for you to shine in the international community. Another one is for you to shine in Brazil. They're very, very different. Okay, completely different. So in Brazil, it doesn't really matter much whether you're following the stream of the international community. It just matters that you publish all the guides here, you have lots of friends, and you're gonna be popular and well known. That's it. And in the international community, that won't be enough.
I was talking to, just to add something, I was talking to a friend of mine, at least, and he's applying for postdoc positions, and he tried in the US. He had a paper with people in the Fermat, for example, but another Brazilian guy, he had 4 papers. And even if these 4 papers were not so relevant, like the first, the one that he did, the guy got that result. Just because he had more, they were in the shortlist, but the other guy got a position.
In US or in Brazil?
US. You will never, I think, you will never got a postdoc in the US if you don't know them.
No.
If you don't work with them, if they do not know you personally. In Europe, it also happens, but I think Europe is more open. Even for second postdoc, for example, Sarah, for example, she could got a second postdoc at Yahoo, also from Unicamp. Now we left the C, but he got a postdoc position.
Where?
I forgot now. I saw in the Roman News, but I forgot now. But it was in Europe. But they will not accept you if you don't work with them there. So for the case of this guy, that's like my friend, he went there, but he spent like 3 months, I guess, or more. The other guy stayed like a sandwich time. That's why I know got the postdoc there. Because he stayed like 1 year, worked with the guys know him. Even if I was maybe let's say, it's not because of anonymity, it's an exception, but let's say there was another guy who had a better CV or something like this. But if they know him personally, like the guy we wrote, American or researching in America, professor tells that he's good, other letters doesn't type from outside America. And you cannot fight against it. That's why you are just another product of the LHC.
Yeah, it matters. So one thing that you should bear in mind, I know it's hard, but in Brazil, it matters a lot the amount of papers you have. But abroad is not that much. It does matter, but not as much. Okay? Not as much. It matters a lot the topic. É outro?
Não, tá certo, mas é porque o chip tá com minha mãe.
E os dois?
Não. Esse outro não sei porque não foi, não. Tá sem sinal, operação.
So anyways, so it matters a lot the recommendation letter. There are some exceptions. So, for instance, let's say, but the Brazilian field is changing, okay? It's changing for good. Why? Because many people who occupy leadership positions in the country today, they lived abroad for a while. So now they are bringing the knowledge and the culture abroad and implementing it in Brazil. So then it's changing. So even CNPq now, CNPq, I don't know if you saw, but when I interviewed Deborah Menezes, who is one of the directors of CNPq for the Brazilian Physics Society, she said explicitly, CNPq will not only count papers anymore. We are trying to put a subject weight on the subject of that paper. And it won't matter the qualities of the paper. It will matter the subject. The subject of the paper, it will matter more. It's harder to judge, but that's how they should do it.
But
It's harder, but
doesn't it make more subjective?
it does make.
But that's how it has to be. I mean,
How has
if you just use numbers,
It's not just numbers.
you just don't count exactly. It's the same thing that we say. For example, I am not a scorer. It's not because in my exam I just got an 8. I am worse than you that got a 10.
Yeah, but there is a reason why there are exams are mostly used and who are represented by a number. It's
But I
not
think
right, but it's less subjective. Wouldn't it be better if you classify better the qualities, like classify more
That's
people
like, for
like
example, in
A,
Europe, you don't have exams, paper exams, in the other grads. All the exams are oral. So they go to the class and the professor asks him something,